Hello everybody, welcome to my home for this computing conference. I am really glad to share with you a project I've done with Guedj and Juliette about nonlinear aggregation of filters to improve image denoising. Images are everywhere, but they are often noisy and so not so easy to use. Noise can have multiple origins, motion blur, information loss or acquisition defaults. We know that several denoising methods already exist, but there are still many improvements to be done. For example, this method can be really specific to a kind of noise, or their parameters can be hard to tune. So in this project, we aim at improving image denoising by combining the existing approaches in a new and original way thanks to machine learning. In this presentation, I will first present the chosen noise model. Then I will introduce the basic denoising algorithm, so the existing method that we will use to create a new one. Afterward, I will present the Cobra model, that is the solution we propose to improve image denoising. Next, I will focus on the evaluation metrics, and then I will be able to share with you the obtained results. And finally, I will quickly present a possible application to automatic configuration. So first, let's focus on the chosen noise models. We will work with 5 different kinds of noise: the Gaussian noise, salt and pepper, poisson, speckle, and random patch deletion. These noises can be seen as a way of damaging an image, and we will try to restore it as close as possible to the original image. To do that, basic method already exists. We have chosen to work with 10 of them: Gaussian filter, median filter, bilateral filter, non-local means, Chambers method, Richardson deconvolution, Lie filter, KSVD, BM3D, and impending. We intend to capture a large range of performance, so we have basic approaches like Gaussian filter, but we also have state-of-the-art approach like BM3D, and we have some general approach, and we have also some really specific methods. For example, impending will perform well on random patch deletions, and the Lie filter will be really efficient on speckle noise. Now let's focus on the Cobra model, that is the method we propose to improve image denoising. The process is really simple. We take a noisy image and we give it to Cobra machines. These machines are just the basic method we have just seen. So we get different estimators that are denoised images, and we will use them to create a new denoised image with a better quality. So this estimator aggregation is really the point of interest of our method. For each pixel P of the noisy image X, we have m different estimators that we denote F1 to Fm, and to compute the pixel intensity of the denoised image, we aggregate this estimator by doing a weighted average on the noisy image intensity. These weights mean that to denoise the pixel P, we average the intensity of pixel Q, such as a proportion, at least alpha, of the preliminary estimators have the same intensity in P and in Q up to a confidence level epsilon. So we have 2 really important parameters: epsilon, that is a confidence level, and alpha, that is a proportion parameter. What is really interesting with our method is that we can compute an upper bound of the error. On average, on all the image pixels, the quadratic error between the Cobra denoised and the perfectly denoised image is upper bounded by the best same error from the basic methods, up to a term which decays to 0 as the number of pixels to -1 by m. Our model needs to be trained, so we started with 25 images that were our ground truth, so without noise, and we artificially added noise, yielding 125 noisy images. Each noisy image is then used to create two independent copies. One goes to the data pool to train the preliminary filters, and the other one to the data pool to compute the weights and perform aggregation. So I've just said that the Cobra model have two important parameters, alpha and epsilon, and we fix their value thanks to a cross-validation approach. For our experiments, we obtain alpha equal to 0.57 and epsilon equal to 0.2. So now let's have a look to the evaluation matrix. So we have everything to be able to denoise an image, but now we have to wonder if the obtained image has good quality or not. So we'll compute 4 evaluation metrics: mean absolute error, root mean square error, peak signal to noise ratio, and universal image quality index. Now I can share with you the obtained results. Our experiments have been done on linear grayscale image. We repeated the process 100 times to really be able to compute statistics. In the following, you will see several times the same kind of picture. You can see 3 images. On the left, the noisy input, at the middle, the Cobra output, and on the right, the difference between the ground truth and the Cobra output. Just below, you have a table with the evaluation metrics. You can see a green line that shows the best denoising method. The red line shows the worst one, and sometimes there is also a yellow line that shows the best basic method. Firstly, we can focus on the Gaussian noise, and surprisingly, the best filter is the Gaussian filter, and the performances of Cobra aggregate are telling when the noise level is unknown. When the noise level is known, Cobra outperforms all the preliminary filter. For the salt and pepper noise, Cobra aggregate is the best. It outperforms all the preliminary filters, even the champion that was BM3D. For BM3D, we have a PSNR of 68.8, and now we have a PSNR of 69. That's an improvement. Next, for the poisson noise, we get the same kind of results. Cobra is the best with a PSNR of 74, and the best preliminary method was Key SVD with a PSNR of 73.2. For the speaker noise, we also reach the best performance, but you can see that the output image is not so satisfying. It is really hard to denoise that kind of image because we have completely lost all the details. So even if the denoised image is not perfect, you can see that in the metric table that we make a huge step forward in the improving image quality. It's really promising, even if it is not perfect yet. Next, for the random patch deletion, we don't have the best performance. The best method remains in painting with a PSNR of 75. Cobra has a PSNR of 74. In the future, this result should be improved. Indeed, in our experiments, we have trained Cobra model with 10 machines, but only one is able to denoise efficiently random patch deletion. We can suppose that if we developed our model by adding other machines dedicated to information loss, we should increase the performance for this kind of noise. Now we can wonder what happens if we put all the kinds of noise on the same image. Let's have a look to this noising image. There are 4 different areas: Gaussian noise at the top left, salt pepper at the top right, poisson noise at the bottom left, and speckle noise at the bottom right. And in addition, we have deleted some random patch. If we try to denoise this image with preliminary filter, we don't get beautiful images. We can clearly see the 4 different areas, and we don't even recognize Lena image. But with our Cobra model, we have made a huge improvement, and we can clearly see the face of Lena, and even if some defaults remain, the quality increase. If we have a look to this table, we can check that Cobra is the best. The best preliminary result was obtained with BM3D with a PSNR of 65. With Cobra, we have reached a PSNR of 67. Finally, we can focus on a possible application to automatic configuration. At the beginning, I've said that basic methods were efficient, but sometimes really dedicated to one kind of noise and with some parameters that are difficult to tune. For example, the median filter is really good against salt and pepper noise, but if the noise rate increases, the kernel size of the filter has to increase too. And so it can be difficult to choose the best value. One possible solution is to train a Cobra model with several machines. Each machine can be a median filter with different kernel size. And for example, with this experiment, we fix this kernel size to 3, 5, and 10, and we get the best denoising result in every case, whatever the noise level was. So it's really a promising example. To conclude, we have presented a generic aggregated denoising method which improves on the performance of preliminary filters, makes the most of their ability, and automatically adapts to the unknown noise level. Thank you for your attention. If you want to contact us, it will be a pleasure to answer your questions. If you want to use the code for your own project, don't hesitate to have a look to this Git repository. And if you want more explanations, you can refer to the paper associated to these presentations. Thank you so much and have a good day.